Hello everyone, welcome to Basic Chemistry Plus, and today we'll be going for DNA block electronic configuration. Right now I am teaching states of matter for the JEE and the NEET students as well. Now, the electronic configuration of DNF block is a very important portion over here. So let's begin. The first point over here that you can see that in the configuration, the last electron is going to the n minus 1 d orbital, which is the penultimate shell. Now, what is meant by penultimate shell over here? Penultimate shell means whenever you see valence shell, that is known as the ultimate shell. Valence shell is known as the ultimate shell. So, what do we mean by penultimate shell then? Now, the penultimate shell are the shells just before the ultimate shell. So, the shell before the valence shell. So let's say I have three shells over here. So this is the valence shell. So this would be our penultimate shell. N minus 1d is the penultimate shell for the Dn for the d block elements. Okay. So what is the ultimate shell then? That is 4s. Over here you can see that n minus d1 to 10, n is 0 to 2. So let's check the electronic configurations now. 1s2, 2s2, like I'm just writing the electronic configuration like you learned, the power principle, the Pauling exclusion and all those things considering. 3p6, then we have 3d10, 3d comes before 4s, isn't it? Because of the n plus l rule. Now 3d is our penultimate shell and 4s is our ultimate shell for the d block element. Okay, but this is also for the ultimate shell. But yeah, this is also for the 3D element. Okay, so n minus 1d, n is 0 to 2. This is how it's done. Now, the transition elements, they have transitional behavior between S and P block. So that's why we call them transitional element, because they have intermediate behavior. Okay. So now, all the transition elements are D block elements, but Zn, Cd, and Hg, they are not transition elements. So what do they mean by this over here? So let's see the right side. So when we talk about a transition element, when we talk about a transition element, an element, so over there, why do we call it transitional? In they have incomplete d orbitals. So the elements, those who have incomplete d orbitals, they are called the transitional elements. Okay, but if you think about Zn, Cd, and Hg, Zn, Cd, and Hg, you'll be able to see for Zn it is 3d10 4s2 if you write the electronic configuration. For Cd and for Mercury, you do understand that it would be just 4d and 5d10 6s2. Similarly, 3d10 4d10 5d. Now you can see that 3d10 is over here, which means it cannot be transitional element because the d block is fulfilled over here. The d block is fulfilled, so we can call them d block element but not transitional element. Okay, they are not transitional element. Now, the first transitional series. So the first transitional series is when we, just a second. Yeah. So the first transitional series, what do we mean by that? From scandium to all the way to zinc. Scandium has atomic number 21 and zinc has atomic number 30. So that's the first transitional element, transitional series. Okay. In there, what type of electronic configuration do we see? In chromium and copper, we see some irregular electronic configuration. So from the first transitional series can be written as this. After manganese, we have iron. Then it comes like nickel, copper, zinc, and all those things. Okay, cobalt. Now 21, 22, 23, 24. Manganese is 25, and this is chromium. Now see the 24. I have taught you a shortcut earlier as well. So it would be argon 18. So 4 comes on 3D and 4s2. So just crisscross 24. So just write it as 42. Okay, 3D and 4s, then write 4 and 2. So you can see over here, this is not the right electronic configuration, although this is what it's supposed to be. Rather, we get 3d5 4s1. We do not get 3d4 4s2. We get 3d5 4s1. Now, why is that happening? Okay, the general electronic configuration should be 3d4 4s2, but we are getting 3d5 4s1. Now, see, this is the 3d orbitals. 5 orbitals would be there, 1, 2, 3, 4, 5. Okay. And 4s orbital, there would be 1 4s orbital. Now, if I draw 3, 4 over here and 4s2, like this, you'd be able to see that 3D is having 4 electrons, right? But 3D 5 stability is greater than 3D 4 stability because of the half filled stability. And you know that, like, if I have half filled stability, I have the highest exchange energy. That's the real reason because behind half filled being stable. So if I take an electron from 4s to 3D, it would become half filled and it would be having the highest exchange energy. So it would look something like this, and you can see that this is the half filled configuration. So this is going to be very stable. Now the spin should be the similar, right? So this is the perfect electronic configuration. So because of the half field stability, 3d4 4s2, that's not the right answer. 3d5 4s1 is the right answer. Similar things goes for copper as well. Now if you see for copper, what happens is copper is 29. So what should be the electronic configuration then? Crisscross. Argon 3d9 4s2. Okay. Now again, this is not the right answer. This is not the right electronic configuration. Now again, let's draw 3d and 4s over here. So 3D has 5 orbitals and there is 4s over there as well. Okay, 1, 2, 3, 4, 5, 6, 7, 8 and 9. You can see, and I have 4s, 2 electrons. So you can see over here as well, if I take 1 electron from 4s to take it to 3D, over here you'd be able to see it would be able to get fulfilled electronic configuration. Okay, fulfilled electronic configuration like the noble gases. So it would definitely want to do that. So that's why this electron do take the jump and comes to the particular orbital, and the 3d10 4s1 is the 4s1 is the proper electronic configuration over here as well. So these are the only two exceptions in this transitional series, first transitional series. Okay, these are the only two things. One is for the exchange energy, another one is the fulfilled stability. Now coming to the second transitional series now. Okay, in the second transitional series, first I have given you the first transitional series as a reference over here. What do you mean by second transitional series? First, let's find that out. So from yttrium to cadmium. Okay, this is the second transitional series from yttrium to cadmium. Okay, if you want to take from want to know what is the atomic number of yttrium, just add 18 with scandium, and for cadmium add 18 with zinc. So you'd get the values. So it would be 48 and this would be 39, right? Now this is the second transitional series. Over here you can see irregular configuration. Just a second. Yeah, over here you can see the irregular configuration is being shown by niobium, molybdenum, ruthenium, rhodium. Chromium, you have seen that chromium and molybdenum would be having the same electronic configuration, isn't it? Similarly, like copper and over there it got cut a bit, but anyway, way copper and Ag, silver. But over here, if you see that vanadium has 3d34s2, but over here niobium has 4d45s1, 5s1. Let me tell you, over here 5s1, here as well 5s1. Only in palladium it is 5s0. So actually, what happens in this transitional series, 5s1 is the most stable transitional element, most stable electronic configuration. Only palladium got 5s0. This is something you need to remember over here. Okay, 4d10 5s0. Other than that, everyone likes to become 5s1. So make sure you keep them 5s1 and write the rest of the electronic configuration. Now coming to the over here, yeah. Just remember all of them are 5s1, nothing else. Now coming to the next one, okay. Again, this is the third transitional series for us, okay. So this is lanthanum, lanthanum, and lanthanum, like below that, this is actinium, this is lanthanum, lanthanum to ZnCdHg, lanthanum to mercury. This is our third transitional series. Over here, so if you just want to understand the atomic number, add 18 with yttrium and add 32 with cadmium. Remember, periodic properties, class 11. So this is how you need to do it. So here as well, you can see chromium and molybdenum has the same old story. But for tungsten, you see, they are completely new. This is 5d4 6s2. Over here as well, 3d8 4s2 and 4d10 5s0. But for platinum, it is 5d9 6s1. And copper remains just the same. Okay, for all three of them, copper remains just the same. So these are the special electronic configuration that you have to remember. This happens because in tungsten and platinum, here what happens is the along with the d contraction, d orbitals, we have f orbitals as well. Along with the d orbitals, we have f orbitals as well. So because of that, we see a new type of anomalous property over here. Okay, 4f orbital we see over here. So this is something we just have to remember a bit. Okay, this is just a short video. So 5d4 6s2, 5d9 6s1, these two are the electronic configuration that you have to go through over here. Okay, so these are the special cases of electronic configurations. Now coming to the next point over here, you'll be able to see that we have just discussed about all these elements over here that you can see. They are showing ND10 and fulfill d orbitals, right? So they should be excluded from the transitional properties, but still they are transitional element. They are kept in d block because of they are showing same chemical properties. So guys, that would be it for today's video. Do watch the next video as well. Don't forget to subscribe to my channel.